Hello, my name is Kevin Ayers. I'm with 3D Metal Consulting, and I'm doing the Miracle presentation. I was asked to do a presentation on where AM Metal is going and doing it in 20 minutes. So everybody say good luck. Perspective is important when you discuss like that. So I've been in the AM space for a long time, since 1993. First with the American FB, I'm sorry? We're early? Yeah, I'm going to go in early if that's okay, because then sometimes I get a lot of questions from this. I expect a lot of ones. So first with the Federal Bureau of Investigation, starting in metal in about 2001 or so in that. Then I worked for Saudi Manufacturing Engineers as their industry manager out of, then Danfoss Power Solutions, which is a Danish-based manufacturing company, putting additive in manufacturing in some 68 or so factories in 23 countries worldwide, using it to supplement production, using additive, mostly in metal. And now I work for 3D Metal Consulting. I've done a lot of design work too and things like that. So this is both hardware and software, materials, hardware and materials. And so I keep track of a list. I have people in my things that help me do that. I'm tracking about 250 companies that make metal machines and sell them worldwide, especially in China. And Senval, if you're not familiar with Senval, they do a database. They help me, along with some of my other people in my network, keep track of these companies, what they're selling, what kind of companies there are. There's a lot of powder bed fusion companies. Most of the market are powder bed fusion. Even though we're going to grow exponentially, I don't think that's sustainable. I think we're going to see some drop off of these companies. I think the long-term markets is too small for powder bed fusion. And the reason why I'm saying that is this is a very slow process. So moving right along. So you guys have seen the charts. I don't necessarily believe things could get a lot of variance, right? In these numbers, depending on who you're looking to. Some say our industry is 12 billion. Some say it's like 28 billion. I think it's on the higher end because a lot of companies and corporations aren't reporting their numbers of stuff they do. And the low end is not reporting what they do, the people's garages and students and things like that. So if you want to count that, but I think the market's much higher than it is. But having said that, until just recently, the OEMs were fighting amongst themselves for these, $18 billion market, which is a mistake. If you look at regular manufacturing numbers, those numbers vary too. But let's say it's, $27 trillion. That's a much bigger market, as you know, for manufacturing. And that's where additive needs to go. And given supply chain disruption we had with COVID and trade wars and shipping parts and companies to have dramatic increases in sales, they need a solution. I deal with a lot of corporations right now. It used to be that you'd find a person who's the advocate, the additive manufacturer within that company. And they're usually in the middle or low end. But now I see corporate executives and presidents demanding solutions to go along with traditional manufacturing. So the new, I think we're going to see is supplementing production using additive is going to be the new niche. People are going to qualify parts with a conventional manufacturing method and qualify it with a additive manufacturing solution. I'm sorry I started early. Come on in if you want to. Are they coming in? I'll wait for them to come on in. So I think, again, supplementing production is going to be the new niche for additive. What I saw in Danfoss, for example, when COVID hit, and later on we had increase in sales, and we were shutting lines down in production. We were shutting down factories sometimes because we didn't have the parts on the operations side. We were losing customers. And how do you put a dollar amount on losing customers? So that's why corporate people are demanding solutions, and most solutions really are additive to complement that. And they want to diversify where they're getting parts made. So some people went to the extreme of buying all their parts in China, and then they got hit here and they couldn't get parts, or the freighters were backed up because they couldn't get labor. So I think that's our new niche as far as metal's concerned. Additive is doing its serial production and supplementing it. Another aspect of that, I can talk about that later, is parts and services and legacy parts. And so if you qualify for a part in normal production and an additive, when you go to make the decision to put that part in parts and services, it's a straight numbers game. In the corporate world, it's a fist fight. People will meet for 45 days arguing about whether to take this part or that part out of production. If you have an additive proven solution that meets the PPAP or other requirements, then it's a straight numbers game. It makes life easier all the way around. And then also have the benefit of customizing some parts when you need to do that. Again, I only have 20 minutes here, so some of the issues with additive, a lot of it really is to do with cost, and some of the other factors translate back into cost. So the overall cost per part in the material, CapEx and additive is a great major part of the cost. The post-finishing, post-processing of the parts to get them within spec for the production part are a big deal. And so those factors thing, again, the normal other things, accuracy, resolution, speed, repeatability, material availability, not just supply chain, but the right metal chemistry, alloys that we need in production. Quality control is a bigger deal when you go serial and additive metal, because instead of doing a lot of 1 every 300 in the check, you need almost to do a 1-in-1 check on quality control. So we're developing more automated processes just for that. And then having the right skill sets in additive can be a problem. People buy a lot of machines without anybody that understands metal, or they don't even have machinists, some of the research universities, so it can be a problem in something like that too. What's happened in the past in additive metal is we went mainly for aerospace applications, some medical. Why? Because you can pay a high price per part. In most industries, that's a no good, but in aerospace, it is. And in a sense, that's held us back as an industry, because most manufacturing is not in aerospace. Those alloys we use in aerospace are not the same alloys we use in production, in automotive, and some of the other industries. So it's actually held us back, and the fact that they could absorb high costs per part has held us back as an industry. The good news is the next gen metal machines can use a lot, thousands of other kinds of alloys that we use in production. Basically anything that's in MIM or powdered metal can be used. And in my industry, we lose a lot of gray iron and ductile iron. And so we can't put anything like that with the material properties we need in additive until just now. So there's a MIM and powdered metal equivalents of everything we're using in manufacturing across the world. So like binder jet metal and some of the other processes are now going to open up the floodgates. So the volume is going to increase significantly, I think, given the supply chain disruption in using additive. And because MIM and powdered metal is cheaper, much cheaper than normal additive metals, the costs are going to go down. So I think we're going to see a major floodgate open up. Lower cost materials are the future, I think. And even aerospace will benefit from that. They're not worried so much about that, but when you start getting lower price, I think you can see that. I'll give you, again, 20 minutes is giving you a time. Equispheres is one of these material companies I really like to watch. Even in powder bed fusion, they're 3 times faster than normal aluminum. They reduce part costs, and it's safer handling. There's less what I call fiddly bits, but you can call it whatever you want, in pieces, shrapnel coming off the parts in the air, less explosive problems along with hazmat, and you get improved consistency in the builds. You get more isotropic parts that way. And much cheaper prices, like I said. Fabric 8 Labs, they're interesting. I'm not really sure how they do this, but the printed copper part is actually cheaper than the copper you can buy on the open market. So there's something black magic. They're using some kind of aqueous solution in copper. Very, very high fast parts. Applications are obviously heat exchangers, things like that. You can build a lot of generative parts in copper this way, relatively cheap and fast, and their technology is very scalable. Optomech. The world changes all the time. The only consistent thing is change is going to be change. And so their process along with directed energy where we can pair a lot of these parts with the same material it was built in. And so this is huge. In a lot of ways, usually the hybrids and some of the other energy, it takes forever to build something from scratch. But if you're starting off with a worn shaft that has spline on it, you're just adding material to it, it actually starts to become economic, especially in parts and services. The microstructure is really good, and there's ways you can cheat and fudge the system to actually get improved material properties when you do that. And also you can print multiple materials at the same time. So you can take a spline shaft, repair the spline. If there was a seal or bearing surface that was going wrong, you can actually print in a better material that would give you a better surface like that. So there's a lot of good benefits from what's going on with the directed energy as well, and some amazing material properties that we couldn't get to before with some of these directed energy systems. I think that's an application we've kind of ignored, legacy parts and parts and services. So anytime you can do these things, you can save costs, and your companies will pay a little bit more for this because they can check the sustainable box. There's if I don't want to go too much on this, but sustainability is a big nail now. A lot of companies give a lot of oral service to this because they want to be able to tell their customers and their stockholders that they're sustainable or becoming more sustainable. But they're not willing to pay a lot more money to do that. But if you can, they are still willing to pay a little bit more if they can check that box in the corporations. Due to the new, I say, worldwide sea change, supply chain disruption is now the new norm. We're going to have this continually. And so companies, I think, are recognizing that. They're looking for solutions, and additive is generally the way they need to go to do that. I think supplementary production, not replacing traditional manufacturing, is a new niche for additive. We're going to be qualifying parts with an additive solution that's in product development along with a normal manufacturing solution, so that when we have problems, we can use it that way. I think technology always goes where the money is to be found. The money is not in the $18 billion additive manufacturing market. It's in the $24 trillion manufacturing market. And that's where we need to go as an industry. And I realize that's a problematic, but we need to adopt all the manufacturing paradigms we normally have to additive and change how we do business. And then I'll skip the rest. But I am seeing the OEMs change. They're contacting the powder manufacturers and asking for much lower material prices. If you look on a curve of when you could build a part in additive, and it's a sloping curve, right? It gets down farther, you can only do so many parts, so much up, reach the prices lower and lower and lower. If you keep that price down, then additive parts become competitive. So there's all kinds of ways we need to reduce costs, and materials is one of them. Went that pretty fast. Any questions? English? All right. Right. Let's try to answer this. I came from the PPAP world. And so that's one of the standards we have, like in automotive, and aerospace has their own, and military. I used to love military standard A10D, but anyway, it's going to take you longer to create the standard and do the test with additive. It is, but you're going to get benefits from doing that. So in one of these standards, different people take part of the test. They're going to have to qualify it. And I mentioned earlier, like lot size testing in manufacturing, you do that. Additive parts, you're going to qualify them one by one. So that is going to be a higher cost to that. That sort of answer your question? Are you saying that we're definitely going to have to do it? I just think it's going to be more intensive labor and cost. I mean, you're going to have to. You can't do it without. Every part is part specific. And so what material are you using? Is it the same as what was used before? That's why it's critical to have these different alloys. You can't have a gray iron casting and then replace it with 17-4 stainless. No way in hell are you going to be able to do that. You can redesign it all you want. It may work, but you're going to have a tough time qualifying it. You need to have the same alloys, same microstructure, same mechanical properties. That's why I think binder jet, some of these other new technologies are the way to go. We've already been using those for manufacturing already. So yeah, you're just going to have to spend the time to qualify those things, and it can be done. I've done them, but it's more intensive because some of that time you have to spend on people, changing their mindsets. And I didn't want to get into when we start doing the generative. We're going to be doing a lot with generative designs. It's just the way it's going to be. But and the good news for the additive world is most of those can only be made through additive. So. That's why powder bed fusion, I think, is on its way out eventually. Yeah, so there is, if I remember right, there's a MIM equivalent of that. Okay, so you can use the MIM equivalent, which is a little bit different, but we've been using it for years in 61, so it will work, and we'll use that in binder jet metal. We definitely won't use it in powder bed fusion, I don't think, because it's too much different. It'll dramatically change the PPAP. You're probably going to have to redesign it if you can get it to work at all. Does that make sense? Yeah, right. So the trouble with, and I cut my teeth on powder bed fusion. I was with the FBI many years ago, and there's just certain things we couldn't use it for because it just didn't have the material properties. It never had the material properties. You couldn't redesign the part to make it work. And so, and there's a inherent problem with powder bed fusion in what alloys it can do, the whole reactive, non-reactive problem. So the good news is the other technologies are starting to work. We're actually seeing production in binder jet metal and some of the other ones now that they're using PPAPs they've modified and they're starting to be done. Now they're keeping that pretty good secret because you have a lot of competition out there. And there's still some problems with dimensional control. But I don't have a problem with dimensional control for most of the designs because, okay, so I spend 4 iterations getting it to the geometry within spec, and build it. Once you've got that, it's repeatable, very repeatable process. So it's not, okay, I'm building 6,000 parts later. Go ahead. The problem I had with those technologies is I could very easily lose dimensional control. And then there was some issues with the microstructure that I saw in the interface level in between, and we had to doctor some of our stuff with that. But all this is promising. I think for certain applications, it's going to be good right now. So, and again, everything is always application-based, isn't it, when it comes down to and then qualifying the part based on the application? Getting back to his question, so it's all three the things that are concerned. Everything's on a case-by-case basis. Well, are we starting from scratch? Or are we starting on deposition on an existing substrate? All right. If you don't have the same chemistry that you're adding the metal onto, all kinds of things can happen. Sometimes it's a good thing, but usually it's not. And I would see micro cracks in the structure on that first level. I know on powder bed fusion on the melt pool analysis, you watch that, and if they try to increase the speed on it, you'll see these micro cracks in the microstructure. And so I would worry about if it's a legacy part on fatigue on that. Does that make any sense? That would be my concern. And you can heat up the substrate, right? And that helps. I would put sometimes micro machine geometries on there so I get the mechanical strength along with what you could call the weld strength on there. Does that make sense? And then sometimes they'll do coatings on there as well that I never had luck with on the substrate, yeah. And so I think additive with, it's not like one manufacturing like MIM. It's 8 to 12, and every month it's a new one, a different kind of metal additive technology. The trouble is we're trying to standardize everything and make it so everybody understands it. And it's a good and bad thing, right? We're evolving so fast that it's hard to keep up on. I have these metal lists. And by the way, I can give you a copy of my metal list of OEMs if anybody's interested. You see a new acronym, that ASTM doesn't have a standard for a new technology. What does it do? No one knows. So it is still, and I hate to admit that it's kind of like a Wild West show as you stay here in the States, but go ahead. I don't think we are. It depends. Of course, it depends on what industry. Right. So let's try to break this up as much as I can. Like, let's look at the binder jet metal, for example. They're using MIM and powdered metal. That has been used in production for 20 and 40 years now, and we understand that real well. And those materials are used with the thing. Now it's got a binder in there, so you got, it supposedly goes away, but the microstructure I've seen there are identical to what you expect from MIM and powdered metal. So I see the path forward going faster than we thought, and given binder jet, I'll probably get in trouble for saying that. Danfoss, somebody waved a magic wand and used some of our powder bed fusion aluminum parts for $5 million, $20 million earth movers because we're out of parts. And they weren't PPAP'd. And so I think that the need, a lot of your engineers and people of science, the need drives you. And we've got needs now. And I think technology is going to go faster than we thought because the need is there. Before COVID, there wasn't a need as much that really drove things. People wanted to think about it, but now the heads of corporations and the people in senior management are saying they're demanding solutions. Yeah. Each print can be different qualifications serialized. Right. But that in some cases the drive might in fact be separate from the need to meet the qualifications. Because again, the market will demand it, or use cases will demand it, or something else, and the technology will be so apparent. Right. So again, I think if I was starting a corporation, I'd start doing it in the product development phase along with it. So it's a lot of that. Its dual activity is complementary while you're doing that. And so, and again, once you qualify, it's ready to go. So, yeah, you are. But again, when you're talking about shutting your factory down or losing customers, which is what we've been seeing happening, right? Then all of a sudden, some people wave these magic wands and they get busy and get it qualified faster than they've ever done before. Now, there's risk in that, I know. But if you talk about companies going belly up, or, then that's going to make people do things they wouldn't normally do faster than they would normally do. Yeah.
Because it makes qualifying easier, even though in reality, you're not
The casting alloy parts aren't the same.
some properties,
Yes, and gosh, I'd say yes and no on that one. So there's all kinds of factors. To give you an example, I had to requalify a part once, the PPAP, and I thought I was using 3D printed sand. All right, okay, it's casted. It's the same alloy. But because you can put internal geometries in the castings to remove air impurity, there was less porosity in the casting, less voids. And so I had to rewrite the PPAP because it's a better, stronger part. I didn't anticipate that. That's not what you're exactly saying, I think, but I think there's, the casted, I think are always going to be there for production because of the price numbers and the infrastructure. But I think where we've got to a point where is we can reproduce the properties of a casted part and actually make it better with some of the new alloys that we're seeing that you can print in binder jet and some of the other new next gen machines. So there is like a MIM and powder metal equivalents of those alloys already, and they're already being used. So it just slight changes. And in the qualifications, you're going to have more work to be done because you're going to spend the extra time qualifying it harder than That's the right terminology used than you would before with the regular casting. But from what I've seen, all the additive parts are much better parts than the casted parts because of porosity and voids and stuff like that. All right. Any other questions? All right. I am saying that. I don't want to say it because we're getting all these new technology all the time. Parts that can be made quicker and cheaper are going to rule the day, okay? Because then we penetrate into mainstream manufacturing. And the promise is there in some of these next-gen machines to do just that. And that's why it's kind of exciting to do with the material properties we need. I don't care, again, I'm repeating myself so you guys can throw food at me, but it's like, you can redesign a part all you want. It's not going to do it. I'm not going to get ductility that I want. I'm not going to get sound absorption from these alloys. They're in normal additive metals. I'm just not going to get it. And again, forget the PPAPs or the standards you have to get. You're never going to qualify those parts out of traditional additive metals that have been there. Guys, argue with me, please. Go ahead. Right. And I don't want to think about natural frequencies involved and how that's changing, the fatigue and stuff like that too. So I don't want to be focusing on binary jet metal, but remember, it's all centered in the end. So that's all going away. It's not a layer by layer melting and cooling. It's melted all at the same time. As long as you got dimensional control, you don't have that issue. You're going to anneal it and everything else afterwards anyway. But I can only look at the microstructure when I'm done. And the ones I've seen, it looks the same. In the testing we've done, you dye it and you look at it in the microscope, and I don't see that. And in powder bed fusion, when you look at that cross section in Z, you can see it, the stress later. You can see it on the welding applications. You can see it on directed energy at times. You can see all that. So I agree with you on that. But I think the promise is there really, if you get away from some of their technology, or they fix them. I mean, they did a lot with the melt pool analysis for the binder jet metal. I'm not binder jet, but powder bed fusion. That helped out a lot. But still, yeah, it's still there. It's just lesser than it was. Is that incorrect from what I'm saying? Or? For which metal additive technology? You have that delta T difference in almost all of them, but not in binder jet metal and some of the other new next-gen technology. It's not there because you're putting it in an oven and you're sintering it down at hopefully an isothermal even thing. So I don't see that in some of the next-gen ones. In the older additive metal, you are. So you're having to convince me because part of that is that delta T, right? And then it's laying the next layer down, delta T, and that's causing strain. But if you've got a three-dimensional object that's binder jet. You're moving the binder, it's melting, and when you're done, you've got a three-dimensional solidified part, not two-dimensional at thicknesses. Yes. Now, I agree, maybe it's not, but from the microstructure slides I'm seeing, I'm not seeing a difference. And it's superior to castings. I'm telling you right now, it's superior to castings. Okay. Thank you.